whoops, I let myself get cut off a little bit in that last video. So we had just done 2 problems using weak acid, HNO2, at 2 different concentrations, 0.25 molar and 2.5 molar and 0.25 molar. And we found that the concentration of hydrogen in equilibrium for the higher concentration was 0.034 molar, and at the lower concentration was 0.011 molar. And I just rounded those numbers that we got in the previous problems. So as we expect, the higher the concentration of the acid, the higher the concentration of the hydronium ion. That makes sense. But what's interesting is that the higher the concentration of the acid, the smaller the percent ionization is. Okay, and that is, I like to think of this as, if I think of like 2 beakers with this weak acid in it. So this one has a higher concentration. So there's a bunch of this weak acid. So it's already too crowded. There's not a lot of space for it to dissociate. Whereas in a lower concentration solution, there's more space. So a higher percentage of these guys can dissociate. So the trend to note is that the percent ionization of a weak acid increases with decreasing concentration of acid. And we can sort of graph this out here if we call this 100% ionization. All right, only strong acids will dissociate 100% and at any concentration. So at any concentration, you'll get 100% ionization of a strong acid. But for weak acids, they don't get anywhere close to 100%. They're more like 5%. I'm going to say this is 5% because I just need some space to draw my line. So at low concentrations, they will have a higher percent ionization than at higher concentration. So as the concentration goes up, the percent ionization goes down for a weak acid. All right, so maybe remembering this trend visually by visualizing this graph can help you remember this rule here. So sometimes that might be asked in like a multiple choice format question. You might be given 2 different concentrations of a solution, and it might say, which one has the higher pH? All right, this one will have the higher pH because it has the higher hydronium ion concentration, but this one has the higher percent ionization. So understanding that sort of trend is important. Okay, so moving on to the next topic. Sometimes we mix acids together. And so finding the pH of an acid mixture, we have to know how to do that. And it's actually pretty simple. Kind of comes down to the strongest rules. I don't know, I just made that up. Okay, so let's say we have a mixture of 2 acids. One is a strong acid and the other is a weak acid. All right, so strong acid dominates there. I even have a rule written in here. The strong acid dominates. So for example, if we have hydrochloric acid, and I don't even know what this one is called, HCHO2. All right, actually that's formic acid. So formic acid is a weak acid, and HCl, hydrochloric, is a strong acid. So when this HCl dissociates completely in water and forms hydronium ions, these hydronium ions are actually going to add product to this equilibrium and push it in the reverse direction. So it's pretty much going to inhibit this weak acid from dissociating at all. It already dissociates very little. And so when we have a mixture of strong and weak acid, it's really only the strong acid that matters, that we care about. So this is the part where I explain that the hydronium ion that's produced by the strong acid will end up pushing the equilibrium using Le Chatelier's principle, and so of the weak acid. And so the hydronium ion concentration is determined entirely by the concentration of the strong acid. All right, So here's an example problem. What is the pH of a mixture of 0.1 molar hydrochloric acid and 0.1 molar formic acid? Okay, so first we need to decide which one is stronger. HCl is a strong acid from the list of the 6 strong acids, and formic acid is not. So essentially we don't care about the formic acid. We just care about the HCl. And since strong acids completely dissociate, if we have 1 molar HCl, then we have 0.1 molar hydrogen or hydronium. That's our concentration of hydrogen ions. So the pH is just the negative log of that. And the negative log of 0.1 is exactly 1. We'll say 1.00. All right, so that's pretty easy. What if we have 2 weak acids in our mixture? Weak plus weak. Well, it's kind of the same story, because even weak acids fall along a spectrum or a range of strengths. So basically, whichever is the stronger acid is going to be the one that dominates. Similar to the above scenario, whichever one is stronger is going to dissociate, and then the hydrogen ions it produces is going to push the equilibrium of the weaker acid to the left anyway and suppress its ionization. So here we go. We've got find the pH of a mixture that is 0.300 molar in HF and 0.100 molar in HClO. It doesn't matter that they have different concentrations. What matters is the strength. So we need to find the Ka for each of these. We look it up on a table. We find the Ka for HF is 6.8 times 10 to the negative 4th. And we look up the Ka for HClO, and we find that it is 2.9 times 10 to the negative 8th. So which one is the stronger acid? It's the one with the larger Ka, which is this one right here. So in essence, we don't give a shit about this one. We only care about the HF and its concentration. But since HF is a weak acid, in order to find the concentration of hydrogen ion or hydronium ions, we need to use an icebox and equilibrium, set up an equilibrium problem. So the initial concentration of the HF was 0.300 molar. It's going to go down by X amount. This is going to go up by X amount. And so these are our equilibrium concentrations for everything. And the Ka, we already looked up on the table, 6.8 times 10 to the negative 4th. So we say 6.8 times 10 to the negative 4th is equal to x squared, x times x, over 0.3 minus x. This being a weak acid with a small Ka, we're going to assume that x is going to be so small that 0.3 minus x is just 0.3. And now we solve. Multiply both sides by 0.3. And we get 2.04 times 10 to the negative 4 equals x squared. Take the square root of both sides. X equals 0.0143. We need to do a validity check. 0.0143 divided by 0.3, our initial concentration, times 100% is 4.7%. So that's pretty high, but it's still less than 5, so it checks out. So it's less than 5%. Okay, so then we've answered the question. We need the pH of this mixture, so we need the negative log of the hydrogen ion concentration, which is X, which is this number here. So the pH is the negative log of 0.0143, and the pH is 1.84. All right, which makes sense. 1.84 is acidic, an acidic pH, and this is an acid, so we would expect it to have an acidic pH. Just common sense checks right there. All right, so for everything that we can do with the hydrogen ion concentration or hydronium, we can also do with the hydroxide concentration. So now we're going to sort of shift over to hydroxide and basic solutions. We've been spending a lot of time talking about acids. So, excuse me. Just like acids can be strong or weak, bases can be strong or weak. So a strong base completely dissociates. There are 6 strong bases, and they are all listed here. For the ones like lithium hydroxide, sodium hydroxide, and potassium hydroxide, when they dissociate, they lose, they have one hydroxide, so they dissociate into one hydroxide. This is where bases differ from acids a little bit. For these 3 bases here, so I'll say calcium hydroxide. When it dissociates into a calcium ion and 2 hydroxide ions. So both of those hydroxide ions dissociate, which is different than with acids, because acids that have more than 1 proton, that are polyprotic, they just lose 1 hydrogen at a time. But bases are different. They lose all of their hydroxides. So it's just these 6 strong bases that you need to know that do that. So if you have 1 molar potassium hydroxide, then you have 1 molar hydroxide. If you have 1 molar calcium hydroxide, it's going to dissociate into 2 molar hydroxide because you have twice as much. For every 1 mole of the calcium hydroxide, you make 2 moles of hydroxide ions. So for a quick practice problem, find the OH concentration for each of these strong bases. So for KOH, when it dissociates, it's just going to have the same concentration of hydroxide, so it'll have 0.225 molar hydroxide ions. And it says find the pH. So I'm going to find the POH first, which is the negative log of the hydroxide ion concentration. So the negative log of 0.225 molar. And that gives us a POH of 0.65. And then I can find the pH by doing 14 minus 0.65 equals 13.35, which makes sense. This is a strong base. I expect it to have a basic pH, and a high pH is basic. For this second one, part B, strontium hydroxide, all right, the concentration of hydroxide in this is going to be 2 times 0.0015 molar because it has 2 hydroxides. So the concentration of hydroxide here is going to be 0.003 molar. So the POH is the negative log of 0.003, which equals 2.52. And so the pH is 14 minus 2.52 because the pH plus the POH equals 14. That's a formula. And so the pH of this one is 11.48. Still basic, which we expect for a strong base solution, even a dilute one. All right, so those are strong bases. Now for weak bases. Weak bases will mostly react with water to form hydroxide. The hydroxide comes from the water, not from the base itself. So a classic example is ammonium. All right, ammonia. Ammonia reacts with water to form ammonium ion and hydroxide. So the hydroxide was actually formed from the water. So the base ion, and this is liquid water, and this would be aqueous, everything else would be aqueous. So the base ionization constant for weak bases is the Kb. Same thing as the Ka, it's just an equilibrium expression. So the NH4 in this case, and the OH minus over the NH3. Water has no place in the equation because it's a liquid, not an aqueous or a gas. So just like with acids, the larger that equilibrium constant is, the Kb in this case, the stronger the base, the more OH it produces, the larger this numerator is. And since weak bases are in dynamic equilibrium, when we see equilibrium, we think icebox. We need to use an icebox to find concentrations. So let's practice this problem right here. So we've got a solution of NH3, which is a weak base. So we write out the equation for it. NH3 reacts with water to form NH4 plus. It's a proton. As a base, it accepts a proton, gains a proton, and it gained it from water, which is acting as an acid in this situation. So since now we can make our icebox. All right, and we've got 4 things here, but since water is a liquid, it's not part of the equilibrium, so we're just going to cross out that part of the table here and ignore it. So initially we have a concentration of 0.100 molar and none over here. This is going to go down by X as the equilibrium shifts to the right and the reaction progresses. So at equilibrium, we'll have 0.1 minus X, and for each of these we'll have a concentration of X. Since we know the identity of the base, we can look up the Kb from a table, and we find that it is 1.76 times 10 to the negative 5th. All right, and we got this from a table that we looked it up. And so now we have the information we need in order to solve for X. And I'm going to do this on the next page. All right. So that Kb was 1.76 times 10 to the negative 5th. And the concentrations of the products were both X. So I'm going to say X times X is the same as X squared. And 0.1 minus X is the denominator. I'm going to use the X approximation technique and assume that this minus X is negligible, so that 0.1 minus X is just equals 0.1. And I'm going to solve. So multiply both sides by 0.1. That cancels out, and I get 1.76 times 10 to the negative 6th equals X squared. Take the square root of both sides, and I get X equals 1.33 times 10 to the negative 3. All right, I need to check whether this was a valid use of the X approximation technique and make sure that the percent ionization essentially is less than 5%. The initial concentration was, if I flip back, it was 0.1 molar. So this percentage is 1.33%. So that's the percent ionization, but it also is less than 5%, so it means that using that X approximation technique is fine, is valid. Okay, so what this X represents is the concentration of hydroxide, in this case at equilibrium. 1.33 times 10 to the negative 3rd molar. It also wanted to know, the question asked, what is the pH? And we can get the pH from the OH, but first we have to find the pOH. So the pOH is going to be the negative log of 1.33 times 10 to the negative 3rd, which is equal to 2.88. So the pH is going to be 14 minus 2.88, which is 11.12. And again, this makes sense because a high pH is basic, and we are trying to figure out the pH of a basic solution, so we would expect it to have a high pH. So if you found the pOH and forgot that you needed to find the, like if you took the negative log of this and got 2.88 as your pH, that should ring weird to you because this is a basic solution. It shouldn't have an acidic pH. And then you'd be like, oh, wait, this is the pOH, not the pH. Okay, so using that common sense check to make sure your answer makes sense is always a good idea. Alrighty, this is actually, no, I'm going to keep going. I still got 10 minutes left on this video. All right, so the next topic, the last topic in this chapter really, are the acid-base properties of ions and salts. And I'm sorry, the resolution of this is not, of this little table is not great. I hope it's better on your end. But essentially, we're looking at a list of strong acids, of acids and bases based on their strength. So at the top here, we have strong acids, and across from them, we have the conjugate bases of each of these acids. So the conjugate base of HCl is chlorine ion. These are ions. That should have a negative charge. And the conjugate base of H2SO4 is HSO4 minus. All right, so pretty much all of these have a minus charge. Some of them have a 2 minus charge. So HSO4 here, all right, HSO4 is a base, but it can also be a weak acid. It's right here, HSO4 minus. And the conjugate base of HSO4 minus is SO4 2 minus. Okay, so the conjugate bases of strong acids are like, they're not even weak bases. They're just like not bases at all. They have negligible basicity. The conjugate acids of strong bases are also not acidic. Okay, so the conjugates of a strong acid or base do not really have any acid or base property. But weak acids, the conjugates of weak acids, do act as weak bases and vice versa. The conjugates of weak bases work as weak acids. So the strength of conjugate acid-base pairs is inversely proportional. The anions, or conjugate bases of a strong acid, are neutral, not acidic or basic. And the anions of weak acids are weak bases. All right, so if we look at these anions down here, we can classify each as a weak base or as neutral. So NO3, that is the anion that comes from HNO3. Its conjugate acid is HNO3, which is a strong acid. All right, so NO3 is neutral because it's the anion of a strong acid, so that makes it neutral. NO2, by contrast, comes from the acid HNO2, which is not a strong acid. It's a weak acid. And so this anion, NO2 minus, is going to act as a weak base. It will act as a proton acceptor. And then this one down here, this last one, also comes from, its conjugate acid would be HC2H3O2. All right, not a strong acid, which means it's a weak acid. And so this ion would act as a weak base. All right, so a lot of negative ions, a lot of anions are basic. Anions are pretty much all conjugate bases of some acid. And if they're the conjugate base of a strong acid, then they have no base power. But if they're the conjugate base of a weak acid, then they will act as weak bases. Okay, so we can determine the Kb of a conjugate base of an acid using this equation here. So Kw is the equilibrium constant of water. which we know is 1.0 times 10 to the negative 14th, at least at 25 degrees. And the Ka is always, the Ka of an acid times the Kb of its conjugate base is always going to equal the Kw of water, the equilibrium constant of water. So for example, we've got an acid here, HC2H3O2, and then its conjugate base, the anion, all right? We can figure out what the Kb is. We can look it up on a table, but we can also solve for it using this equation. And so if we just write the Ka times the Kb equals Kw, all right? We know this, and we know this, and we need to figure out this. So I'm going to rearrange this equation so that we're solving for Kb, because that's easier to me. So that would be equal to Kw divided by Ka. So Kw is 1 times 10 to the negative 14th, and this Ka, 1.8 times 10 to the negative 5th. So that means that Kb equals 5.56 times 10 to the negative 10. All right, so we figured that out using this equation here. If you know the Ka, you can figure out the Kb of the conjugate base, or vice versa. So the same is true, like we said that for an acid, a weak acid, the conjugate base of that weak acid will be a weak base. But we can do the same with the reverse. The cation, the positive ion of a strong base, is going to be neutral, just like the anions of a strong acid were neutral. And the conjugate acid of a weak base will act as a weak acid. So for example, this one, like sodium hydroxide, is a strong base. When it dissociates into sodium and hydroxide, all right, this sodium is neutral. It does not have any acidic quality. But for ammonia, which is a weak base, ammonia, which is a weak base, all right, its conjugate acid is NH4+, which does act as an acid. It's a weak acid. Okay, so for each of these ions down here, these cations, we're going to classify them as neutral or weak acids. So Na+, that is the cation that comes from the base NaOH, which is strong. So that means that this ion, Na+, is neutral. All right? Other neutral ones would be potassium from potassium hydroxide. NH4+, I just did that one as an example. That is the conjugate acid of NH3. And NH3 is a weak acid, and so that means that that NH4 is going to act as a weak base. Sorry, NH3 is a weak base, so NH4 is going to act as a weak acid. And then Ca2+, what base does that come from? It comes from calcium hydroxide, which is a strong base, so Ca2+ is a neutral ion. It does not make a solution acidic or basic, whereas NH4+ does make a solution slightly acidic. It acts as a slight acid. And so with these different ions, these cations and anions, we can form salts. Remember, a salt is just an ionic compound that's made of a cation that's positively charged and an anion that's negatively charged. And then when it dissociates into solution, when you add a salt, a soluble salt to water, it dissociates into that cation and that anion. So some salts are actually a little bit basic or a little bit acidic, depending on what cation and anions form in solution. And that will be the topic of the last video.